Tom, for a wonderful introduction.
Yeah, right.
Everything he said is absolutely true. We're extraordinarily distinguished. With that out of the way, I want to begin this conversation tonight with a question of why are we here? And by that I don't mean like why are we here in Vintage Forum. We all know why we're here, but why are we here more broadly? What is the sequence of events that led to the emergence of advanced life on this planet? And of course, in some sense, this is a biological question, right? You could imagine asking that question and answering it in a biological fashion. But just as the, say, researcher at Caltech does not really happen without the context of the institute itself, I would argue that the more fundamental question, or an equally fundamental question, is to ask the question of what are the physical processes, what are the astrophysical, chemical processes that lead to the emergence of environments in which life can form. So with that said, we will move away from the picture of the Chinese balloon here and take a broad look at the solar system. After all, the Earth is not isolated, right? The Earth is not the only object that orbits the sun, and the architecture of the solar system looks like this, with the planets indeed on this diagram shown to scale, right? So this here is the sun. We have Mercury, Venus, Earth, and Mars. A few asteroids in between, and then as we move away, we have Jupiter. Jupiter is the most massive planet in the solar system, clocking in at 300 Earth masses, followed by Saturn at 90 Earth masses, and the two somewhat smaller ice giants, Uranus and Neptune, at 17 each. I should mention that beyond Neptune, there's also a collection of icy debris my distinguished colleague here discovered, all the important ones out here. And if you were to go far beyond what the projector allows us to do, you would, as Tom mentioned, find Planet 9 well beyond the water over there. So I like this picture because it demonstrates to you that the solar system, right, structurally, really is subdivided into two groups of planets. There's kind of small things that are rocky, right, have very thin atmospheres, that are close to the sun, and if you go far beyond, there's really, really large objects. But at the same time, this particular picture is deceptive, because what it hides is the orbital architecture. So let's take a look at that, okay? So here we have the sun in the center, Mercury, Venus, Earth, Mars. Actually, if you look very closely, my house is right there. And we have Jupiter, Saturn, Uranus, and Neptune. Jupiter is 5 times as far away from the sun as is the Earth, and Saturn is about 10, Uranus is about 20, Neptune's at 30. Okay, and you really begin to appreciate the fact that the terrestrial group of our planets really is quite close. It's this compact sequence of rocks that live seemingly much, much closer to the sun than do the giants, right? For the longest time, this was the blueprint of planetary systems, right? Dating back 400 years, people have tried to look for planets around other stars with this as the blueprint. And if you do that, there's really 2 ways that you go about doing that search. Number one, you look for the most massive things. You would look for the analogs of Jupiter orbiting other stars, and you would look for that by kind of the slight periodic reddening of their host stars with a period of about 10 years, the time scale it takes for Jupiter to revolve around the sun once. Alternatively, if you're trying to find something like Mercury, you would just stare at the night sky and measure how bright the stars are in hopes of measuring a dip where a planet goes and eclipses one right? Those are the two methods that you can use to try and find planets around other stars. The problem, even though people have attempted something like this for about 400 years, it hasn't been until the last 30 that the technology of telescopes came into sharper focus where you could actually carry out this exercise. So starting with 1995, okay, now to be clear, this is after Nirvana broke up, but before Britney Spears made it big, okay, so that's give you a scale, okay? So during that decade, right, we found the first planet orbiting a sun-like star. And since then, right, we have experienced an explosion of this activity, right? This diagram here shows you all of the planets that we have discovered to date. We have approximately 5,000 of them now in the galactic planetary census. And looking at this diagram alone, ignoring this text, which is typeset at 0.1 font for your readability, you know that there's the whole spectrum of planetary objects. There's big ones with rings, there's kind of smaller, kind of Neptune-sized things, there's a bunch of rocky-looking worlds. So you have the full spectrum of planetary system. But just like that picture of the solar system, which didn't show you the orbits to scale, this picture is misleading, okay? Because it doesn't show you where the orbits are. So let's take a look at that again. Okay, so this is projecting all the planets that we found to date around their host star. Of course, they don't all orbit the same star, right? They all orbit their own individual stars, but putting them all in orbit of a single object for just visualization, this is what the currently known galactic planetary census looks like. And if you're a careful observer, you might be like, that star looks really big, right? I'm not sure it looks big compared to the planets. It's the same, question as like, are children small or are they just far away? Right? No, they're small. So this is the staggering thing that we found out. Okay? This is the galactic planetary census. All the planets we know of today. This is the orbit of Mercury, the closest thing we have to the sun in the solar system. Okay? Venus, Earth, and so on. Right? We're not the average outcome, clearly. Most of the things we found to date complete a single revolution around their host stars in a matter of days. The kind of outliers over here, for them a year lasts a whole couple weeks. But most of them just orbit their stars in a matter of days. And it's just a staggering, it's just a staggering discovery, right? What does this mean? This means that all of our understanding of how planetary systems emerge, which has for the last 100 years been constructed to reproduce the solar system, is just plain wrong, okay? Because the solar system, as it turns out, is kind of maybe a little bit weird. This is the standard outcome of the planet formation process throughout the galaxy. Okay? So, again, just without being a phenomenal statistician, you can kind of just look at the kind of objects that orbit their host stars, and you can find that there's big ones and small ones. And a little while ago, my friend Andrew Howard, who's a professor of astronomy at Caltech, and him and I were hanging out, and he asked me, he's like, okay, if you were to construct a planetary system out of the census of the planets we've discovered, what would you see? And I said, well, I don't know, you'd see some big guys, you'd see some small guys, they'd all be pretty close to the host star. And he said, wrong. Here's what he found. Okay? He said, yes, if you take all of the discoveries that we've made today, put them in a bag, and start drawing randomly, you would get great diversity. But if you examine each planetary system in isolation, what you see is extraordinary intrasystem uniformity. So there's something about the planet formation process that creates a great variety of planets. But once the particular star chooses what kind of planet it's going to create, it's like a factory. We'll stamp one after another of the same type of object, both in terms of planetary spacing, in terms of mass, in terms of radius. So this is yet another discovery that adds a moment of true confusion, because this is so different from the solar system itself, right? As we discussed in the first slide, right, the solar system has a vast variety of objects. So what's going on here? And so inspired by that conversation, I thought about it quite a bit, and I thought, okay, there's somewhere we've seen this kind of thing before. Okay, like this is eerily reminiscent of another thing that we know of in astronomy. And in fact, this is eerily reminiscent of literally the first discovery ever made in astronomy. Okay, and that is the discovery of Galileo Galilei when he adopted the telescope as a scientific instrument in 1609 and looked up at the night sky. Right, he first looked at the moon, but okay, we don't need a telescope to know the moon is there, hopefully, right? And then he looked at the other thing that's bright. He looked at the brightest thing out there, which was Jupiter, and then he drew this. And I want to draw your attention now to the fact that Jupiter itself is encircled by 4 other stars. It's very weird that Galileo's drawings are so pixelated, but it's the kind of technology. Yeah, he didn't have Microsoft PowerPoint. So what are these? These are the Galilean moons. Okay, the moons that encircle the planet Jupiter. What's interesting about them? Well, first and foremost, these objects orbit Jupiter in a matter of days, just like extrasolar planets. Secondly, if you were to take them, okay, and take Jupiter itself as well as its satellites and blow them up such that Jupiter becomes a mass of the sun, and you were to ask what kind of planets would these become, they would be the typical extrasolar planet, a few times more massive than the Earth, and yet a few times less massive than Uranus and Neptune. So even though the solar system itself seems a little bit weird, the satellite system of Jupiter, right, looks like a miniaturized outcome of the standard outcome of planet formation throughout the galaxy. Okay? So inspired by this, we decided to look into this problem more closely. Now, both planets and satellites do not just appear in isolation, right? They appear during the first few million years of the lifetime of a star, when stars are encircled by these thick disks of hydrogen and helium gas as well as dust. And this is not a picture from 4.5 billion years ago. This is an artist's rendition from one of our models, but the young Jupiter would have looked something like this, where it was encircled by this cloud of hydrogen and helium gas, which also had a substantial dust component. And what we found out early in our work that dates back now a few years is that even though we were, of course, none of us were there 4.5 billion years ago, one of the things that we can do is to use our understanding of the laws of physics to recreate what the formation of satellites of Jupiter must have looked like. Okay? And what we found is that the Jovian disk of hydrogen and helium, right, stuff that surrounded the young Jupiter, was an excellent trap of dust. So dust grains, right, much like the ones that are floating around this room somewhere, would get trapped in this disk of hydrogen and helium gas around Jupiter, and subsequently, once their mass became large enough, they would collapse into to basically icy asteroids. Okay? And subsequently, upon this system of icy asteroids that orbit Jupiter in a kind of a ring would unfold, right? Their gravity would cause them to stick together and grow into the satellites. That said, once the satellites reach a critical mass, the disk starts to pull them in. And if you're carefully watching the outcome of this computer model that we've done, those orbits are slowly shrinking, right? And that is a key element, okay, that we've discovered, is that if you let this whole system unfold, right, let it evolve under its gravitational and hydrodynamical evolution, there exists a critical mass scale, right, that once reached allows the orbits to leave their feeding zone and stop growing. That's why Io, Europa, Ganymede, and Callisto, the satellites of Jupiter, live close to their host stars. Okay? And that's why they're all kind of the same mass and the same size. They grow up until the disk pulls them in. So we were pretty excited about the kind of outcome of all this, the ability to, in a nearly perfect manner, reproduce the architecture and the masses of the Galilean satellites. And we immediately thought, upon figuring this out, that, okay, what happens if we now apply this understanding to planetary systems more broadly, okay? And here, it helps to take a look at the photos that we have of young stars, okay, and the disks that surround them. So these are all stars younger than 4 million years, okay? And you can see that they're encircled by disks of stuff. And in particular, all of the solid material, the dust, goes into these rings, just like in our computer simulation a few slides ago. So what happens? Well, this is a picture from a paper that we just published literally a couple of weeks ago. But rather than explaining this specific picture, I'll show you a video of what we obtained. Oh, see, I'm just not good at clicking. Okay? Like, I keep going back and forth. Okay, we're gonna try this one last time. Okay, now it's gonna work. Okay, so this is an outcome of one of our computer models where the dust self-consistently collects into this ring, and within this ring, a planet emerges, but upon growing to a sufficiently large mass, gets pulled in by the disk. And this leads the way to the second one forming, and so on and so forth, which leads to the emergence of large-scale uniformity among the planetary systems that was discovered by my colleague, Andrew Howard. Okay? So all of this is here to tell you that somehow the process that makes the moons of Jupiter and the process that makes typical planets that orbit other stars is the same process. But I believe I'm yet to answer the question of why is the Earth different? After all, the Earth's orbit, if you haven't noticed, lasts a full year. It doesn't last 3 days, right? So why is it that the Earth escaped this particular evolution sequence? And the answer is simply that within the sun's protoplanetary disk, right, the disk of hydrogen and helium that encircled the sun during its first 4 million years of lifetime, the ring of solid material from which the Earth emerged was low mass. Okay? It was so low mass that it took the Earth longer to form than the 4 million year lifetime of the hydrogen and helium disk. Instead, the Earth took hundreds of millions of years to form. Why? We think we understand the answer to this. And we think that the answer, the culprit, as to what makes the solar system special is actually Jupiter. Because Jupiter, upon forming, right, cleared out this giant gap in the solar system's disk and prevented the flow of solids from replenishing the Earth's local environment. So with this thought, I want you to think about the following, right? What this suggests is the fact that the presence of giant planets like Jupiter is kind of a prerequisite to the emergence of low-mass planets like the Earth. If Jupiter was not there, then our Earth would evolve to be a big multi-Earth mass body that would capture a huge hydrogen-helium atmosphere, and then we wouldn't be able to do astronomy, okay, because we wouldn't see the sky. Okay? Moreover, that none of the sunlight would penetrate down to the Earth, photosynthesis wouldn't work. Right? So perhaps the fact that we are having this conversation is something that we owe to the emergence of Jupiter, at least if this theory is correct, which I totally promise it's totally right. So with this thought, I actually want to hand this over to my friend and colleague Mike, who's going to dive even deeper and discuss further.